Thank you very much for the invitation by the organizers to attend this workshop. I have found it very informative up to this point, and I would also like to thank the co-authors of this paper that are well known to many of you. My colleague Peter Kotze, who also serves on YAGA. He is the head of our geomagnetics group at the Hermanus Magnetic Observatory. And Peter Sutcliffe, our previous manager of the Hermanus Magnetic Observatory, who is retired now but is still an active researcher at our laboratory, and the primary author actually of the work that I will present here in terms of the neural networks. This is an overview of an historic development that was an incident for Peter Sutcliffe and actually laid the foundation for lots of subsequent research at our institution. This may be the last time that you see this name, Hermanus Magnetic Observatory. There is some new developments in line which I will address later on in the presentation. A brief overview of my presentation. I will give you some background on the Magnetic Observatory and the research we do at the observatory. We have recently been designated as the Space Weather Regional Warning Center for Africa, and I will give you some information about our Space Weather Center. We are in a very special location with respect to the South Atlantic anomaly, which drives a lot of our research focus, and I will indicate how we are situated with respect to the South Atlantic anomaly. I will then address some aspects of artificial neural networks and show you some brief results and future plans. Thank you. The Hermanus Magnetic Observatory, which several of you have visited in the past, is located in a small town 100 kilometers east of Cape Town. It is part of the worldwide network of magnetic observatories. We do research for on geomagnetics and on space physics to monitor the near-Earth space environment. We do both fundamental and applied space physics research. We have a large group of students involved in our activities at the observatory because we have recently become part of the National Research Foundation, for which the main output is scientists, not magnetic data. But we still also provide geomagnetic field-related services to the industry and the military on a commercial basis. A brief history. We were established in 1932. I thought we were a very old observatory until I heard about some of the Russian observatories that are hundreds of years old. But we are very proud of our continuous record of observations from 1932, when the Magnetic Observatory was established at the University of Cape Town at the request of then the International Polar Year for having some southern hemisphere observatories that would be do continuous measurements during 1932-1933. By 1936, Cape Town had developed to the point where there was an electric railway, and as in many other places, the observatory had to find a quieter environment, and the then director of the observatory had a vacation house in Hermanus, and he sought out the environment to test whether it would be appropriate to move the observatory there. And so in 1941 the observatory was moved to its present location in Hermanus. In 1960, for some time it was part of the Department of Physics in Cape Town. Then it moved to our Department of Land Affairs for mostly mapping purposes. In 1969 it was taken over by the Council for Scientific and Industrial Research, and the focus then was commercial development of magnetic devices. And in 1996 the observatory became a member of INTERMAGNET with 3 stations contributing INTERMAGNET data. In 2001 we were declared a national facility and transferred to the National Research Foundation which brought in a total new focus on the work, and you will also see that from the activities that will follow. And in 2011, we will become the space science branch of the South African Space Agency, which was very recently established. Just a little bit of history. In the second International Polar Year on the University campus of Cape Town, up on Table Mountain, the first observatory housing, that was the place where the first continuous measurements were made with Lacour measurement instruments. This was the location where it moved far away from the center of what was then Hermanus. This is now very close to the center of the Hermanus today, but many of these buildings are still in operation. Thank you. We have expanded our research observatories from Hermanus to other Southern Hemisphere locations. South Africa has a base on Marion Island here in the Indian Ocean on the mid-oceanic ridge, a very interesting location for geophysical observations. In 2000, that location has been used for biological research for a very long time, since 1948, but it was only in April 2007 that we re-established some instruments there for ionospheric research, and we hope to expand that to geomagnetic research. On Gulf Island, we are the only occupation entity. It belongs to the United Kingdom, but we are renting the space there for our observatory on Gulf Island, where we have also put up some GPS receivers for ionospheric characterization. And then, since 1960, South Africa has been active in Antarctica at the base Sinai 4, 72 degrees south. In December 2006, we expanded our activities there with the establishment of, for the first time, of a absolute magnetometer, the Hofrauser, and also the subsequent year by the installation of an FGE. This is just our base in Antarctica, now established on the rock, where the previous bases were all under the ice and have disappeared. This base has a lifetime of 20 to 30 years and is very well equipped. Our nearest neighbors in Antarctica is the Germans on the western side, and the Russian station Novskaya on the eastern side. This is our base on Marion Island. The base has recently moved from an old base from 1948 to the new base that you see on the hill there, which is very well equipped for research. Thank you. The core activities of our observatory is geomagnetism. We have the geomagnetism group under Peter Kotze, which monitors and studies variation of the Earth's magnetic field, derives various models, regional models and indices, and distributes the geomagnetic field information to our various stakeholders. We have a technology group that was established during the time when we were part of the Council for Industrial and Scientific Research, and this technology group provides services in the magnetically clean environment and also does calibration of compasses for, among others, the defense and the aerospace industries. We have also developed a number of products, such as this one, which is a compass test facility to test compasses that will fly in aircraft before they use these compasses for compass swing operations, which are very expensive. Since 2004, the Space Physics Group was established. The Space Physics Group came from the recognition that the external influences on the magnetic field have a very interesting right for study in themselves. There were several attempts at the establishment of a space weather center. Peter Sutcliffe had made such proposals many years ago, but in 2004 the Space Physics Group has been established and has now grown to be our largest group of activity at the Magnetic Observatory, looking at the various dynamic processes in the space environment and their effect on space weather. This is the latest addition to our activities. We now have a space weather regional warning center, which was established in 2007 by the request of the International Space Environment Service. And we have a space weather website that provides real-time space weather warnings for the local community of most of all the communications HF radio users, and the center has just been established in December 2010 and opened by our Minister of Science and Technology. Thank you. This is just a snapshot of our Space Weather website, spaceweather.hmo.ac.za, and some of the data products that we are make available on our website. We have geomagnetic real-time data for Hermanus and Sana'i, our Antarctic station. We have ionospheric data from ionosonders, from GPS-derived total electron content, HF propagation conditions, warnings and predictions, and some information about our instruments. And one can get the real-time data from spaceweather.co.za and warnings from the site. Thank you. This is just the data from last night to give you some indication of the fact that we actually do get real-time data. I don't want to have the internet link right now, but yes, it shows the activity of the magnetic field from our FGE and our overhauser in Hermanus, and also some indices that we derive in real time. And it is for the purpose of deriving these real-time K indices and also other indices that we have done some modeling of the quiet time field so that one can establish the deviation from the quiet time field. The dxdy and dxdt and dydt is of interest for our GIC warnings for the power utilities. And we have similar data derived from the Sana'i station, which is on our website in real time. Thank you. Some of the other space physics research that we are involved in, we are part of the SuperDARN network. We have one of the SuperDARN stations in Antarctica, and this is mostly used for magnetospheric tail dynamics and ULF waves using those radars. We have the work of Peter Sutcliffe is now focused on theoretical studies of waves and plasmas, studying various pulsations and comparing ground data with the satellite data of the JAMP and cluster. We are involved in ionospheric tomography, which is the focus area of my research, where we use dual frequency GPS observations to also then characterize the ionospheric electron density. And then the work on which I will focus in the rest of my presentation, the modeling of various phenomena by means of neural networks. We have several people working on modeling the ionospheric parameters, HMF2, FOF2, and the long distance propagation conditions using neural networks with various inputs. And next slide, please. In terms of geomagnetic field modeling, we have an array of repeat stations, of about 40 stations around the Southern Africa and Namibia and Botswana that we annually visit. We have continuous recording from 4 stations, Ketman's work being the latest addition to our continuous recording stations. From these indices, which are sent to the World Data Center, the DST index is derived, and we are one of the key contributors to that index, and we typically have about 2 million requests for our data per annum for the derivation mostly of these indices. We still continue to do the magnetic declination maps, as we have done in earlier days for our mapping department, and also then provide the annual change maps for prediction. Thank you. This is part of the interesting place that we are. The magnetic field in Hermanus has been declining ever since the first observations made in 1942 at Hermanus by about 20% to date, and it is still decreasing. At the other stations that have been joined later on, we found the same trend. The mean declination exhibits the jerks that we have seen in the recent history, 2003 being the most recent one over here, and also the increased rate of change in the annual mean declination on 2 of our observatories. A very interesting phenomenon here that the northern observatory in Tsumeb, which is west of the zero line, there the declination seems to be increasing. Another interesting reason for our studies is that we are very close to the South Atlantic anomaly. The chart here is the difference between the maps derived from the Ørsted and MagSat satellite observations, 1980 and 2000, and we are here close to the region of maximum decrease in the magnetic field, but also not very far away from the region of maximum increase. And Marion Island lies approximately in between, and that was one of the reasons why we're eager to establish some magnetic observations on Marion Island. This is the South Atlantic magnetic anomaly expressed in terms of the US-UK World Geomagnetic Field model, EPOC 2005, for the total intensity. And the center of this is over South America, but also reaching out to approximately our Cape Town Observatory, our Hermanus Observatory. If one looks at the horizontal intensity map from the same model, then the horizontal intensity is at its lowest in this region, much closer to Hermanus. Now the artificial networks. An artificial network is a model of the human brain, mimicking some of the attributes of the human brain to take multiple inputs, to process those inputs using neurons, and then to derive some composite output based on a nonlinear combination of those inputs. The various contributing factors to the parameter of interest are presented on the input layer, which may have as many nodes as there are known inputs. There are one or more hidden layers, which are called neurons, that have associated with them each a weighting factor, a multiplication factor, that weighs the inputs of the input layer, and then these are projected onto the output variable, and the process of training this model is to present a large amount of input data, use some algorithm to train the weights on the hidden layers, and using the output to estimate the correctness of the model by comparing to measured output variables. The work in neural networks started at the Magnetic Observatory in 2000 with Peter Sutcliffe writing up a paper about the regional geomagnetic daily variation model, which is what I will also present here. And subsequently, the new director of the Magnetic Observatory did a PhD under Peter Sutcliffe on a neural network approach to doing ionospheric modeling of the bottom side electron density over Grahamstown. Her PhD student, Elijah Ujemi, worked on an F2 global model for ionospheric electron density, and several students subsequently worked under the supervision of Leanne McKinnell and myself on neural network applications to total electron content, solar cycle prediction, prediction of geometrically induced currents, then the occurrence of spread F on the ionosonders, and then also in these two theses, the one on topside modeling of the ionosphere and total electron content modeling over Southern Africa using GPS data, which also feature neural networks. Thank you. In space physics, artificial neural networks have been used particularly successfully for time series prediction in cases of complex systems where there are some patterns, but the physical links between the causes and the consequences are not very easy to determine. They are especially effective in modeling time development of irregular processes such as magnetic storm and disturbance indices. And here we use the artificial neural network to model the irregular part of the daily variation of the magnetic variation due to what is thought to be mostly E-region ionospheric currents driven by the dynamo action. The observatories, the recording stations in South Africa are at Hermanus, Hartbeeshoek, Tsumeb, and Keetmanshoop. For this study, we are only looking at the older of these 3 stations and using the data from these 3 stations also to incorporate a latitude dependence in our model. Thank you. Some data about the observatories that we have considered in this study. Hermanus, Tsume, Barbesup, and Kitmanshoop. The Hermanus data from 1941, Tsume from 1964, Barbesup from 1973, and here are the latitudes and longitudes, and also geomagnetic latitudes of these stations. Kitmanshoop was established in 2006 with equipment donated by GFZ Potsdam, and it has qualified as an intermagnet station only in November 2009, so we do not yet have a long record from data from that location. In this study, we compared the efficiency of the artificial neural network with that of the harmonic analysis, which was conventionally used for patterns. Now, in this case, one can express the total field or any other component of the field in terms of the daily mean, the DC component, and then the regular SQ variation. And the SQ variation can be expressed in terms of a number of harmonics. Typically 1 to 4 harmonics are required. But for every season and for every station, one needs a separate model of this kind with estimation of these various parameters, the amplitude and the phase. It is this irregular part that is also captured by the artificial neural network. Okay. So in this case, the artificial neural network is a feed-forward network, which the inputs are hour, day, magnetic latitude, sunspot number to represent the solar cycle, and the AK index to represent the activity. And it is a fully connected network, and the output then is the hourly mean values of either the total field, horizontal field, or the declination. This is the components then. We used 7 input nodes for the 7 parameters with hour and day of year represented by continuous functions by converting it to a sine and cosine, so one does not have a discontinuity in the data. And the hidden layers were adjusted until we found the optimal number of hidden layers for the observed output of interest. Thank you. The data we used for this was for the period 1978 to 1989 over 1 solar cycle. And then for testing, we used a period in the subsequent solar cycle that was not used for the training of the neural network. The weight training was done by backpropagation algorithm by Aitken. The weight updates were accelerated by the delta bar delta algorithm on Bishop. We trained data from 3 observatories with a spread in latitudes over a 12-year period, but we excluded data for KB above 5 from our training set so as to keep it to quiet time data. And the output data, which was used for training the algorithm, was the middle of every month, so day 14 and 15 was not included in the training data, but used for the testing of the algorithm. And these are then our results. For very quiet times, K less than 1 for Hermanus, this is all Hermanus data. The neural network and harmonic analysis models performed fairly similarly. There was no big difference between them in comparing with the observed data. We used here 6 days for which K was very quiet during 1993, and for this case they were very close to each other. For the next case, we observed some days with K between 2 and 4 in 1993, and with some more variability on the data, it was found that the neural network did much better than the harmonic analysis. In fact, the RMS difference was 9% better for the neural network than for the harmonic analysis. Next one. So in conclusion then, our neural network modeling has shown that the daily geomagnetic field variation can give results that are comparable to that of harmonic analysis, including latitude and seasonal dependence, and it is better than the harmonic analysis model in terms of operating sunspot activity and magnetic activity. Future projects, we are going to install, as was mentioned by Karapanov, some of our 1 Hertz instruments from his institute at our 3 long-term observatories. We will continue neural network modeling for our 4 observatories to incorporate the other observatory in our model. We will also look at the modeling of the horizontal component of DBDT for the GICs. We are working on the re-establishment of Geomagnetic Observatory Station on Marion Island. There was an observatory many years ago, 1972, Peter Sutcliffe established it, and we want to go and re-establish that. And your interest and collaboration on any of these are very welcome. Just a little bit about the Marion Island, 1972. This was Peter Sutcliffe working there on the island to establish Magnetic Observatory, which ran until 1980. It had been replaced by a Doris hut for the Doris system, but the pillar is still there from that original observatory, and that is the location where we want to go and put a magnetometer just to measure the variation to see for whether we can get correlation. I was there in April 2010 to go and make a survey of the gradients in that area, and this is where that pillar is, and hopefully we can reduce the magnetic signature of this Doris hut by removing some of the steel cables. Thank you very much. In April 1, 2011, the HMO will become the space science branch of SANSA.